Hello everyone. In this lesson, we will discuss series IL circuits. A circuit contains a resistor and an inductor in series with a voltage source is called the series IL circuit. An inductor or a coil is a device in which changing current produces an opposing voltage. The ability of the inductor to induce voltage by the current buildup in this case is called the inductance. The unit for the inductance is in Henry and symbolized as H. The formulas for the current to calculate this current in this RL circuit during the current buildup is presented as I equal to E divided by R multiplied by 1 subtract E to the exponent of negative L divided by L over R. Alright, so before we move on any further into learning how to calculate certain components in these formulas, I would like to remind everyone that this is an RL circuit in series, right? So you see right here you have I as the current, E as the total voltage source, R is the value for your resistor, and 1 minus E is the irrational number E, we know about that, and T is time, L is the inductance, and R is the resistance. So it involves all the components that we are discussing in this case, in this series IL circuit. Again, this formulas right here is quite complicated to derive. It involves differential equations, which we have to learn about derivative, about integration in order to come up with these formulas. So in this class, what we have is we just need to know the formula, and we will learn how to calculate certain components in these formulas. Alright, so before I continue on further, I would like to remind everyone that in previous lesson we are talking about the time constant, right? Okay, so let's discuss the exponent of this number E. In this number E that we have, with the exponent, I have negative T over L divided by R. Okay, so I wrote it like this so that I want everyone to remember that it will be L over R in the brackets. Alright, so that means you want to perform this operation first, and then you divide that value into T. Again, you have an inductance measured in Henry, you divided by resistance measured in ohms. How can you match the unit with the time? In order to eliminate the unit, then you can take E to that certain exponent. So in this RL circuit, the times constant is divided by L divided by R. Okay, so this step is very important. I always recommend that everyone to perform this step first so that you can simplify the number. You can skip the step and key everything into your calculator all at once, but I don't recommend that unless you have to provide a lot of brackets and really know what to tell your calculators. Alright, so therefore, in most of the steps that I'm showing everyone here, my step number 1 is always finding the time constant. Alright, okay, so you see that this equation is an exponential equation again, and involving number E, so we have to learn how to calculate that, and later on we are going to have to solve for time, and you know that in exponential equations, excuse me, then we have to involve the logarithm. In this case, it's natural logarithm, in order for us to solve for the exponent as the time. Alright, so let's get started. Example number 1. In charging a series IL circuit, E is given as 30 volts, and R is given as this certain amount, and inductance is this certain amount, and I can tell everyone that I present this as 3 significant digits in this case. Determine the current given time equal to that 0.5 second after the switch is closed, right? Okay, so step number one is always calculating the time constant, which is L divided by R according to these formulas. So let's write it down beside all our calculation here. So I will write it as I equal to E divided by R. Okay, you see E divided by R by itself is Ohm's law, right? But because of the RL circuit, it has this component attached to it, 1 minus E raised to exponent negative t divided by time constant, and time constant for the RL circuit would be L divided by R. Okay, so we will make sure that we base on this formula to do all the calculation, and we follow order of operations, right? Alright, so first of all, take 400 divided by 5000. I end up with these values again. I don't work with engineering notation, so I just have ohm, I just have Henry. So my answer, I can have it in second. So if you turn on your um, calculator and put it in engineering notation mode, you will see that it turned into 80 millisecond. 80 millisecond is the same as 0.0800 second. And I write it in three significant digits just to remind everyone. So after I've done that, you see this number, I substitute it in here. I put it this number right there, right? Okay. So then I take negative 0.5, I divide it by 0.08, I have negative 0.625. So take a look at this step on its own. Step by step, we reduce a lot of calculations, complicated thinking in what do we do with the bracket using the calculator. So up to this point, if you want to skip all of this step, you can use your calculator if you know the algebra well. But I want to explain to everyone that BEDMAS, you have to perform everything in the bracket first, so that be in the bracket, then the exponent. You see e raised to this exponent negative 0.625. If I use my calculator, it will give me this value, 0.535261429. I try to write as many as I can to present it to everyone, so that at the end we round to three significant digits, then it's more accurate. So the next step is to perform whatever inside the bracket. That means I have to take this result away from 1. So take 1, subtract this number. I will have a value, and that value multiplied by 0.06 will give me this number. Okay? So, but if right here, if you just key this in to your calculator, also using the bracket, the calculator will realize that, alright, I work with the subtraction inside the bracket first. After I get that result, I'm going to multiply by 0.06. Okay, so if you give a proper bracket to the calculator will know that it has to follow the rule of BEDMAS. Alright, so after you get this number, you can round it to three significant digits and also present as engineering notation as well. Okay, so let's move on to the next example. In this case, I will have to do the reverse, right? I have to do the reverse by finding the time. Okay, so again, I want to rewrite that formulas for everyone so that we can make sure that we know the process in this case. I equal to E divided by R according to Ohm's law, but because it's an RL series DC circuit, so I am going to have the components that 1 subtract E to exponent of negative t divided by the times constant is L divided by R. Okay, so this formula should be written like here, so we can quickly refer to this while we are working on all of the calculations. Okay, so this example asks me to in charging an RL circuit, E is given as 15, R is as 3000. So if you key this into your calculator, it should be 3K, right? If you use engineering notation. The inductance equal to 9 Henry. At what times will the current in the circuit reach that amount? because we are build up the current here, so we have to uh, 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 have some times. We have to give it some time so that eventually it will reach that certain value of current that we need to achieve. All right. So again, step number one is always finding the time constant, and time constant is L divided by R. So I take 9 divided by 3000. I have 0.003 second. If your calculator is in engineering notation, then you will find that is equal to 3 millisecond, and it's the same as 0.03 second. Okay, so if you keep your uh, calculator in engineering notation mode, at the end you still get the same answer as mine if you do it correctly. But I just want to be very clear to everyone here, in case someone doesn't want to use the Casio FX991MS and don't have the engineering notation feature on that calculator, they can just do this and then they can convert at the end. Okay, so let's get back to step one again, right? We are finding times constant. Uh, Divide these two values, we have 0.03. Then I take the 0.03, I substitute into the exponent for e. Okay, so now I leave it like that because I have to solve for t in this case. So the rest of the number is I reaching 0.03, so I substitute it on the left hand side of the equation. E is 15, R is 3000. Okay, so this is when I want to explain to everyone why I have 0.6 on the other side. Alright, okay, so I just want to remind everyone that I am using this concept. I will time that with 3000, bring the number across the equal sign. I change its operation. So that's one way of solving for an equation as well. You change the operation when you move the number across the equal sign. So right here, I divide it by 3000. I bring it over, I multiply by, and here, so you see you multiply by 15, you bring it over, you divide it by 15. So if you perform this operation, it turn into 0.6. Okay, so just take your calculator and do that. You will see that 0.003 times that with 3000 divided by 15 will give me 0.6. So at this point, I clear whatever surrounding the brackets, because you see you are solving for an equation. So you want to, at the end, you want to isolate the unknown, but your unknown is the exponent, right? Okay. So my next step is I perform this step. I actually put e, bring it across the other side. Instead of negative e, it turns into the positive, okay, or adding the t on this on this side, the e to this exponent negative t over 0.03 on this side of the equation, and I bring the operation of plus or adding the 0.6 over to the other side. I subtract 0.6. That's why I get 0.4, and on the other side I just have e raised to the exponent of negative t 0.03. Okay, so you probably ask me why I am doing this, because you can only apply logarithm to the e when your e is actually a positive value. Okay, so you cannot apply logarithm to a negative of e. So when you have a positive of e, then by itself, and then a number by itself on the other side, then you can go ahead and take natural logarithm on both sides. Like in previous video, what we have learned is natural logarithm or logarithm is an operations. So if you perform operation on this side of the equation, you do same thing on the other side. So at this point, I want to remind everyone this. So we have natural logarithm, that means log of the base e, and then e to the negative t of 0.003. So you see that this is 0.03. I make sure that I have to write it properly. 0.003. So now you see this process, this can be eliminated according to what we learned in previous class. So you eliminate the entire thing. Now your exponent as the unknown can be just a simple linear equation for you to solve for t. So on this side, you just have a fraction, negative t divided by 0.03. On the other side is natural logarithm of 0.4, right? So natural logarithm of 0.4 can be easily calculated. And when I punched it into my calculator, I got negative 0.91629072, and um, bring the negative 0.03 over to the other side of the equations. I multiply by, and at the same time I can write this as so negative t over 0.03 is similar to t over 0.03 as a negative. Alright, so what I do is I bring this operation across the equal sign, so I multiply by, divided by, I multiply by, and when I multiply these two, negative times negative, here negative times negative should give me a positive values, and in engineering notation and also in three significant digits, I should have 2.75 millisecond. So if you keep your calculator in engineering notation, you should end up with the number in engineering notation as well, which is millisecond in this case. Alright, so don't forget this is real time. Therefore, the answer should always be as a positive value. If you ever done the calculation and you end up with a negative time, just to make sure that you go back and trace your step, because I think that it will be incorrect, because you should have a positive values at the result. All right, okay. So again, I didn't mention to everyone. I actually remind everyone of these formulas right here. Okay. So when I highlight, it's happened to be highlight the whole thing. So anyway, um, I would like everyone to try this exercise number 2. It has a lot of questions for you to work on. And number 1 to 3 is basically finding the I. Okay. Given that, and if I say, if I don't mention like in charging an R series IL circuit up here, then it's also meant that I'm charging an IL circuit. Okay, so everything is listed here for everyone, and the answer is actually given for you as well. And where do you find the full solution for this? The full solution for this is right after this handout. And you can find the solution. This one is exercise number 2. So the solution for exercise number 2 is also typed here, starting on page 7. All right, okay, so everything is typed for you. So if you have any problems getting the answer, or the solution, the full solution step by step are written here for everyone. Okay, so I just hope that everyone will not have any particular problem with this at all. So I just want to remind everyone that in almost every single solution, I always start with finding the time constant. Okay, so finding the time constant, and then simplify your calculation and going from there. All right. Okay, so I don't think I have anything else to say, except for asking everyone to make sure that you work with the exercise, um, knowing the key on your calculators, the natural logarithm key, the e to the exponent key, and the negative sign, and make sure that you work with engineering notation, and find the times constant first. All right, thank you.